Good morning, everyone. This is Mrs. Rondo. We're going to be looking at a new type of transformation today called dilations. We'll get into that in a minute. Our essential question: what are dilations and scale factor, and how do we identify them? The learning goals: I can test the properties of dilations on a given figure, and it does clarify in that learning goal the properties of dilations that we're focused on are preserving angle measure and side lengths are proportional. And then the second learning goal, I can determine the scale factor as a number greater than or less than 1 based on whether the dilation is longer or shorter than the pre-image. It's nice and wordy, but it actually isn't too bad. Let's go ahead and jump in. So dilations. A dilation is a non-rigid transformation that changes the size of a figure but not its shape. So you might want to pause at different points here to write these down. So this is different than rigid motion. If I can remind you about what a rigid motion transformation is. So rigid motion only changes location. Only changes the location. And we have, for a rigid motion, we have size and shape are the same. So they keep the same size and shape and only change location. Dilations are different. They are non-rigid motion. And specifically what's going to change is the size. So the size of our figures is going to change, but not the shape. So we should maintain the same look to our figure, just the size is going to be different. So that's a key, that only the size is changing. Then we have the center of dilation. That's a fixed reference point that we use to help us reduce or enlarge a figure, make it bigger or smaller. So reducing is making it smaller, and enlarging is making it bigger. And again, you might want to pause to write down some of this, as I know the notes don't have a fullness here. They have part of it, but you got to fill in the rest. All right, and then the last one, the scale factor, which we use the letter K to represent scale factor. This is the ratio meaning a fraction, ratio of side lengths for the image to the pre-image. So here's what that looks like. We say K equals, and you definitely should write this down, the image over the pre-image. And just a reminder about what those words mean, image and pre-image. The image is the copy and the pre-image is the original. So just another way of remembering that. All right. And so we have properties for dilations. These are the three here. And again, you might want to pause to just write those down quickly. Dilations preserve or keep. So this is what they keep the same. So they change size. I'm going to make a note there because we talked about that with rigid motion, what they keep and what they change. So they change size only. That's the only thing they change. But they keep the same angle measures. Collinearity, this means points on the same line. Okay, so if I say 2 points are collinear, it means they're points that are on the same line. So when we say for dilations that we preserve collinearity, that means if I start with a figure that has 2 points on the line, then when I change it, do my dilation, those 2 points will still be on the same line. And then the last one is orientation. This one is kind of like saying direction, like which way your figure is facing. And we'll see that in a minute. All right, so here we go. This can be found, these pictures can be found on page 579 of your textbook. However, you pretty much should be good just typing into your Google Doc. So here we go. Example 1, determine if the transformation is a dilation. If so, give its scale factor. So we're going to do that by going through those properties. So does it preserve angle measure? So as I look, I'm wanting to match up like A to A prime, because remember A would be the original. The ones with the primes, those are the copies or the after result. So the original is the original letters A, B, C, D. And then when we do a transformation, then we put in those primes. So when I look at this angle here, and we're going to do this just by looking, although it is possible to measure and check it. It appears that A to A prime, the angle measures are the same, and we would check that for B, C, and D. We're going to say yes, and just trust Miss Rondo. I don't like that normally, but we're going to trust that they are the same. If you want to get out a protractor and measure them, go for it. They are the same. Preserves collinearity. So A, for example, point A and point D are on this same segment. And when I look at A prime and D prime, oh, look, they're on the same segment. So yes, preserves collinearity. And we would be checking that for all the sides and points, but hopefully you can see that that's true. Preserves orientation. This means that we are facing the same way. In our case, do the figures preserve orientation? No, they do not. This would be some kind of reflection. It has flipped over. It's no longer facing the same way. If it was the same orientation, it would look something more like this. Same orientation would be, it has to have the same basic, that's horrible. But hopefully you get the idea. The image here, the copy, the end result has been flipped over. It's some kind of reflection. So the answer there is no. So is it a dilation? Because we had a no, then it is no, it's not a dilation because we didn't preserve orientation. And so then we are not going to worry about scale factor because it's not a dilation. And it's really bothering me that my picture is not a little bit prettier. Sorry. All right. So let's go ahead and that's a little better. Okay, move on. So example 2, determine if the transformation is a dilation. If so, give it scale factor. So same process here. Preserve angle measure. So if we look at, again, A to A prime and the other angles as well, we're going to say yes, it does. Looks like it does. Looks to be the same shape. Preserves collinearity. So again, that's testing the points. Are they on the same line? Yes, they are. A, B, and A prime, B prime. And it works for the others as well. So yes. Preserves orientation. Are these triangles kind of pointing the same direction? Yes, they are. They both have the same. One of them isn't, flipped or turned or something. And then is it a dilation? Since we had all yeses, the answer here would be yes. And then we need scale factor. So unfortunately, this example is not great for figuring out scale factor. Scale factor, we're looking at the length of a side compared to the length of a side. But since these are all diagonal lines, we're going to use slope to help us out. So then scale factor, since it was dilation, we're going to find the scale factor. For this problem, the scale factor is going to be a little weird. So scale factor, first of all, is we use the letter K, and we talk about image over pre-image. But for this problem, for the image over pre-image, those are usually the length of a side compared to the length of a side. Unfortunately, the way that this picture is drawn, we can't easily find the side lengths. So we could find them, but it would take quite a bit of work. So we're going to just actually look at the slope. And so we're going to use a different method for scale factor that's just looking at slanted lines. So if I compare the slopes, I want to see what did I do from the original figure to get to the copy. So if I start with my original figure, I go up 1. Looking at slope from A to B, I go up 1 and over 3. So that slope is 1 over 3. That's for my pre-image. It's my original. Then what did I do to that to turn it into whatever I'm going to get here for my image? All right, so I start at A prime and go to B prime. So I go up 2 and over 1, 2, 3, 4, 5, 6. So up 2 and over 6. So how did I turn 1/3 into 2/6? I did that by multiplying top and bottom by 2. So my scale factor in this case would be 2. So I had to multiply all of my original values by 2. Again, this one is a little bit weird. We'll practice scale factor more in a minute. So if you're like, what? Don't stress it. We'll do it more in a minute. Okay, determine if the transformation is a dilation. Explain how you know. Okay, and this one doesn't say to find scale factor, but we're going to do that as well if it's a dilation. Okay, so we're going to kind of look at this. What do we think about example 3? Does it preserve angle measure? Yes, it appears to. Does it angle measure collinearity? Looks good. And then we're looking at, I'm sorry, I totally blanked. Orientation, there we go, orientation. So yeah, it looks good in all of those ways. So if I go to find scale factor on this one, so we would say yes for the determine if the transformation is dilation. Yes, since all the properties are true. Okay, and then we would create the scale factor. So we're going to actually find the scale factor. This one is a lot more normal in terms of what we normally do to find scale factor. So remember, scale factor is going to be image over pre-image. Okay, and so I'm going to look at my shape for a side that I can easily count. And so that would be either CD or DE. Now on the original figure, both are fine, but if I look at the copy or the image, C prime to D prime is fine, but D prime to E prime, I have this spot where I don't quite know what the value is because it's not at a perfect corner there. So I'm going to look at C to D. So C to D right here is 2 units, and I'm going to compare that to C prime to D prime, which is 3 units. I'm going to put that into my scale factor. Now be careful, it's image over pre-image. Image means the end result, which was 3, over the original, which was 2. So our scale factor is 3 over 2. And there we have it. All right, on to number 4. So that is, again, much more normal for how we find scale factor. Number 4, this one, looking at all the properties, do we have angle measure? It looks like maybe the one that I would really question is the C right here. Are those two really the same? I don't know, but collinearity looks good. Looks like I have the same points on the same lines. Where I have a major issue is orientation. So this one would be no, since the triangles have a different orientation. Now, it's probably also true that the angles don't quite match up, but this one is clearly the orientation is different. We have one, we might say right side up and upside down. And then that will leave it there. All right, our last one to look at is below is a figure from example 5. This is what we just looked at. What is the center of dilation and where did my lines go? Oh, there they are. Okay, so sorry. So this figure, to find the center of dilation, essentially what you're going to do, and you're going to see, actually, I'll let that first line go, is this line is drawn here because it connects E to E prime. So basically you go through and connect all of the matching letters. So A to A prime, B to B prime, C to C prime. And we see what happens here. So D to D prime, E to E prime. I'm sorry, that was B to B prime, excuse me. And then my A to A prime and C to C prime. So what we're looking for is when we do those connections, the point where all of those cross is our center of dilation. So that's how we find it, is we connect up the matchy letters, and that gives us our center of dilation at 0, 0. All right, that's it for today. You guys have a great day. We will see you later.